Hello everyone. Today we'll talk about what's called the row-column rule for matrix multiplication, and I'll mention a couple other matrix operations. Let me recall from last time that we have this idea of matrix multiplication. So if A is m by n and B is n by p, right, we can make sense of AB as, by definition, this is going to be a m by p matrix, where I get the columns by taking A times those columns of B. Right? So this will be the first column. The second column of this new matrix is A times B2. I do this for all of the columns of B, which there are P many of, and I get a new matrix. Okay, this is how we defined things last time. So today I want to talk about kind of a trick for computing individual entries of AB. i.e., so this was the notation we had last time. If I want to know just the entry in row I in column J of this matrix. So this is the entry in row I, column J. Okay, so here's the trick. I think I'll just write it down and then we'll do an example. So this is what he calls the row, or the authors call the row-column rule. So write this down in words, and we'll kind of see this in a formula, and then we'll do an example. So the entry in row I, column J, of the matrix AB is, so it's this kind of mouthful again, it's the sum of the products of the corresponding entries from, so here's why it's row column. So first from row I of A, and column J of B. Okay, so that's a mouthful. It should look familiar. This is kind of the same sort of process we had when we were taking matrix times a vector. In fact, that's a special case of this. But in general, if you take matrix times matrix, you want to know what's the entry in row I, column J of the product. So let me just write this out in symbols. If I want to know what's the entry in row I, column J of the product, right? So what I'm doing here, let me draw kind of a cartoon that might help a little bit. So here's A times B, right? Here's A times B. It equals a matrix that's, well, this is AB. So if I want to know what's the entry in, say, row I, column J of this, right, that's of the resulting product, what I do is I take row I of the matrix A and column J of the matrix B of the right-hand side, and I do that thing where you you take the products of the sum of the products of the corresponding entries. So in symbols, what this looks like is you take A, right, this is AI1, AI2, up through AI. How many columns do we have in A? I didn't write this, but okay, we assumed it's N. And then I multiply it by B1J down through B. How many rows were here? There was also N, right? So what I get is AI1 times B1J plus AI2 times B2J plus, keep going until I get AIN BNJ. Okay. A lot to take in, but let's do an example. I mean, I think you'll start seeing how this goes with an example. Let me do kind of a big example just to see how all the various indices are coming into play. So let's see. Let's see if we can fit it all onto this slide here. So e.g., let me take 2 minus 5, 0, minus 1, 3, minus 4, 6, minus 8, minus 7, minus 3, 0, 9. Yeah, this is A, and I want to multiply it by a matrix B. Let's say 4 minus 6, 7, 1, 3, 2. Okay, so what is this? A is 4 by 3, and this is B, which is 3 by 2, right? And so we can multiply this because the number of columns of A equals the number of rows of B. This will be a 4 by 2 matrix, right? You kind of cross off the middle, you get a 4 by 2 matrix. There's going to be 4 rows, 2 columns. This is AB. Okay, and the idea now is if I want a particular entry, I then pick the corresponding row of A and the column of B. So let's say we want AB in, I don't know, row 3, column 2. Okay, so that's row 3, column 2. I want this entry here. So what I do is I take row 3 and column 2, and I do this thing that I was saying before. I take the sum of the corresponding product. So this is 6 times minus 6 plus minus 8 times 1 plus minus 7 times 2, which is, okay, kind of a big negative number. This is minus 36, minus 8, minus 44, minus 14. I think that's minus 58, so big negative number. Let's do maybe one more. If I wanted, say, I don't know, the second row, first column, so this is now AB. I'll remove this here. So if I wanted AB, say, second row, first column, what I do is, second row, first column, and I do the same corresponding sum of products. So minus 1 times 4 plus 3 times 1. Oh, sorry, I was doing the first row. 3 times 7, right, the first column here. Plus minus 4 times 3. And what is this going to be? This is minus 4 plus 21. So that's 17 and minus 12. I think this is 5. I did that right. Yeah, minus 12, minus 6 is minus 16. Yeah, that looks good. And that's that entry. Okay, so yeah, this is a trick now that you can now do this for all the entries of the the matrix here, and you get all the entries. But again, if you only wanted certain entries, this would be a lot quicker than the previous definition. Okay, so changing gears a little bit. So further properties of matrix multiplication. Again, I'm not going to list them all here, but this is theorem 2 from page 99 of your text. I'm going to write these out kind of without being too precise here, but the matrix multiplication satisfies many things that are familiar from our usual arithmetic. So for instance, there's an associativity that says if I take A times the product of BC, that's the same as AB times the product with C, the product of AB with C. This is sometimes called associativity. I should mention that when I write these down, right, of course, I only do this when it makes sense, when the number of columns of B equals the number of columns of C, the number of columns of A equals the number of columns of B, etc. You also have a distributive property, so remember, we can also add matrices. It turns out that if all the shapes of the matrices are correct to make this make sense, then we have a distributive property. You can also distribute scalars, meaning if I take a real number times AB, this is the same as RA times B. These are kind of distributive properties. Properties. But I want to point out that one of our familiar properties of real numbers does not hold here. So in fact, AB is not equal to BA in general. So this is not a commutative operation. This multiplication of matrices is not, right? So this is weird because you guys are used to probably 4 times 2 is equal to 2 times 2 for numbers. But here in the world of matrices, that breaks down. And let me kind of show you an example. If you take A to B, just as kind of a arbitrary example here, but just to show you how in practice what this looks like, so these are both 2 by 2 matrices. So this means that AB and BA both make sense, right? Because you can multiply a square matrix times another square matrix of the same size. But what do you get for AB? Let me just do one of them. So this is going to be a 2 by 2 matrix. The entry in the upper left is going to be 10 plus 4, right? I'm taking the first row and first column here. So that's 5 times 2 plus 1 times 4 is 14. The entry in the first row, second column will be 5 times 0 plus 1 times 3. and I get 6 minus 8, and I get a 0 minus 6. And you can check BA is 10 to 29 minus 2, not equal. Okay? So again, even when the two products make sense, AB and BA, they're actually not the same matrix, which is, probably the first time you've seen something like that. The last thing I just want to write down, just to kind of complete this chapter, is there's this notion of a transpose. So a little bit changing gears again, but let me give a definition. If A is an m by n matrix, its transpose, that I write AT, is the n by m matrix whose columns are given by the rows of A. Okay, so all I do is I take that, it's kind of a simple-minded thing. It seems kind of silly to do this, but we'll see why it's important later in the class. I just take the matrix and the given matrix A, and I just take its rows and make them columns of a new matrix. So I think probably easiest to do this with an example. So if this was, some matrix you gave me, what is A transpose? So this was a 3 by 2. This is now going to be a 2 by 3, and I just take, that first row and make it the first column. I take the second row, which was 1 minus 3, make it the second column. The last row becomes the last column. That's it. That's the transpose. Okay, again, we'll make use of this later in the class. Right now, it's just a definition. Some properties I want to just write down, and we might talk about in discussion a bit more, is what happens when you take the transpose of the transpose? Well, that's just the same as taking A, right? Because if I make the rows the columns, which then I make the rows, I'm back to A. Another not too hard thing to see is that if I take the sum of two matrices and take the transpose, I might as well done that transpose thing to each of the matrices and added them. It also plays well with respect to scaling. So if I take the scalar of a matrix and take the transpose, that's the same thing as scaling the transpose. And then finally, which is maybe the most interesting one that I won't prove for you today, but what happens when you take the product of two matrices and take a transpose? Turns out that you actually want the product of the transposes, but in opposite order. Okay? So I think I'm out of time. I was planning to maybe prove this for you, but this is something we can talk about in class. Maybe you guys can kind of think about this. Can you prove why that is? It's kind of funny that you'd get this switching the order, but if you work it out, you'll see why. Okay, so that's it for now. We'll see you next time.